Welcome guys. So in this video, let's prove this snake lemma. Okay. So this snake lemma should be the first, the number one first theorem in the homological algebra, and very commonly used in the algebraic geometry and algebraic topology, and which is the most tedious proof and the difficult proof in the So basically, it's not the difficult. I should say it's tedious. Yeah, so you can go to Wikipedia and see this is the snake lemma. Don't worry if this is the first time you see it. Yeah, so basically you have three R module, or basically if you is a abelian group or so-called abelian category, and you have F and G, F prime, G prime, ABC, and these are short exact. These are right exact, these are left exact, and there will be a Z sequence from kernel A to kernel B to kernel C, co-kernel A, co-kernel B, co-kernel C. Yeah, if you see this diagram, if you plot kernel A here, co-kernel A in here, and you will see this is kernel A, B, C, co-kernel A, co-kernel B, co-kernel C. So this is so-called, this is why this is so-called snake lemma. Yeah. Okay, so in this video, let's prove the snake lemma. Yeah, the proof will be very, very long. And if you go online, then you will see the snake lemma proof. It's very long. So you can use the so-called spectral sequence to prove it. But the spectral sequence should be like a more advanced technique, which should be derived from snake lemma. So we should come from we should just do we should start from the scratch. So let me just quickly remind you guys that now we only view A as A to A prime as abelian group, and the kernel A, and the kernel A means that the X belongs to A such that so such that A of X is 0. So basically, it mapped to 0 cokernel, and the cokernel A is just defined to be A prime modulo image A. Okay. Yeah. So kernel A, B, C, cokernel, and you connect it. And the theorem say that the least line is exact. Okay, so this is actual theorem I copied from Wikipedia. Okay. Okay. Yeah, and this D is very famous. This D means that we need to connect this kernel C to cokernel A. Okay, now this is called so-called connected homomorphism. If you learn about the algebraic topology of Allen Hatcher, then you will understand these words. Very basically, if you learn about algebraic topology, then you will connect the homology group of X to Hn minus 1. Yep, it's fine. Maybe we will talk about algebraic topology in the future. Okay, so let me just quickly set up notation. Okay, so this is the step one. So step one is proof everything is consistent. Okay, so let's see. You have A, B, C, 0. Okay, my notation is that A prime, B prime, C prime, alpha, beta, gamma. Yeah, and this is 0. Okay, and my notation is a little bit tricky. I define this is F, and okay, I define this is FA, this is FB, this is GA, GB prime. So this is called GA prime, GB prime. Okay, so bad notation. Yes, and I want to show that the kernel A, kernel B, kernel C goes to cokernel A, cokernel B, cokernel C goes to, yeah, this is, I want to prove that this is exact. Okay. Actually, if this is 0, then it should be 0. If this is 0, then it should be 0. Okay. But yeah, and let's denote the definition. Let's say this is KA, and K. So I should define K. Oh, sure. What hell is going on? This should be alpha, K alpha, and K beta and gamma. Sorry, I'm stupid. Yeah, this should be alpha, beta, and gamma. Alpha, beta, and gamma. notation. Yeah, this is alpha, beta, and gamma, alpha, beta, gamma. And I define this k alpha, this is k beta. So kernel to co-kernel, this map is just divided by delta. Yeah, this is the common notation. And I call this is C. I call this is let's see my notation. Yeah, I call this should be C alpha and C beta. Okay. Okay, so I want to show that kernel alpha, K alpha, kernel beta, kernel gamma, K beta delta, and co-kernel alpha, co-kernel beta, up to co-kernel gamma, which is 0. So C alpha, C beta. Okay, so theorem, this is next lemma. This lemma is exact. This sequence is exact. But by the way, you can see there's a in the movie there. I think it's there's a snack lemma showing some movie. Okay. Okay, so yeah, so remember a notation. Okay, so you can write this diagram in your book so that you will not forget about it. Okay, so let's see. So let's quickly see the definition. So let's say, okay, so let's define a K alpha, right? K alpha is kernel alpha to kernel beta, and the K beta is a kernel beta to kernel gamma. Okay, so this should be trivial. Okay, the reason is that that's let me just change the color. I just don't like this color. Yeah, so we need to derive this, right? So let's see kernel alpha is some element here, right? So it's easy to get the kernel. It's easy to get from alpha to kernel beta, right? Just composite with this FA. Okay, so simple object. Just define this K alpha to be your FA restricted on kernel alpha, and your K beta is a FB. FB, right, restricted on kernel beta. Okay, so simple idea. Let's say if alpha belongs to kernel, if A belongs to kernel alpha, then your beta FA commutative diagram, right? So it's GA prime A alpha A, right? So, and this is 0, right? Because means that diagram is commutative, and the this means that this also this GA prime is a homomorphism, right? So if your alpha A, by the definition, alpha is 0, right? So this guy will be 0. Okay, so that means your FA restricting to kernel alpha will be in the kernel beta, right? So that means we prove this definition is all correct. Also, this is the correct. Okay, so now we need to. So now we already have these two objects, right? We already defined these two. So now we need to get the cognative homomorphism. Okay, but before we define a cognative homomorphism, let's define these two. Okay. Okay, so now we need to define this C, right? So this remember that the co-kernel alpha is defined to be A prime minus image alpha, right? And your co-kernel beta is defined to be B prime image beta, right? This is just definition. So now we need to define a C alpha from co-kernel alpha to co-kernel beta. Okay, so simple enough, right? If you have a co-kernel here, it just composite with GA prime, right? So simple enough, right? So it's easy to get. So let's define yeah, so let's see. So if your C alpha act on A prime plus image alpha, right? So this is the co-kernel, should define to be GA prime A prime plus image beta, right? And the same for the C beta. Okay, so these two are well defined. Yeah, so these two, no, so this is just definition, right? In order to show this is well defined, it's a little bit tricky. Yeah, because you need to. Okay, so let's see. So let me just show the C alpha is well defined. It's well defined. Oh, by the way, this next lemma proof is very lengthy. Okay, so if you have A1 prime plus image alpha equals to A2 prime plus image alpha, right? Then you know that the A1 prime minus A2 prime will be in the image alpha, right? So that your A1 prime minus A2 prime will be alpha A for some A in A. Okay, so once you have this, then you take this GA prime, A1 prime minus A2 prime will be GA prime alpha A. Because it's just right from here, right? And then it's just commutative, so you get the beta FA A, right? So which is beta FA A. This FA is what? FA is you send it here, right? So it's in the image. FA is in FA is something, right? But econ beta, so this guy is image beta, right? So which means that their boundary or their difference is 0 in a co-kernel beta. Okay, so same reason for you to exercise to show C beta is well defined. Okay, so finally let's define a connected homomorphism. Okay, so this is the most cumbersome one to get the definition. So kernel gamma go to co-kernel alpha. Okay, so basically the important snake part. Oh, by the way, subscribe to my channel. Thanks. Okay, so that's maybe let's see C beta kernel gamma. Okay, so right, so let me just write down again. So we get this. Oh, we all have this, and alpha beta gamma FA FB GA prime GB prime. Okay, so let's see if we get this, right? See here. Okay, we can see to be the kernel gamma, and we need to connect it to kernel A alpha, right? So somehow like we need to change snake, we need to twin it a little bit. Yeah, we know that this row is exact, right? So exact means that image become kernel, right? So if this there are C mapped to 0, then you can find B. So simple enough. So this is onto, right? So this map. So basically FB is onto. Or basically if you are a troublemaker, then you can say it's epimorphism. Yeah, so maybe I will talk about a category theory in the future. Yeah, so you can find the B belongs to B such that your F of B will be C, right? And we know that the beta B will be something B prime, right? And the C becomes a kernel gamma. So we get the G B prime beta B will be just the definition, right? Will be gamma F B B, right? This is just commutative diagram. And that will be gamma C, right? Because FB by definition your FB is C, so this is gamma C. Okay, so gamma C is what? Gamma C is 0, right? So that your beta B belongs to kernel of GB prime, which is image of FA prime, right? So that means you can find something in A prime. Okay, so there is A prime in A prime. Okay, so I can define this A prime's answer. Okay. Yeah, so this A prime is. So I can define that your connected homomorphism delta C just be A prime plus the image of A. Okay, so exercise for you to show this is well defined. This well defined is a little bit tricky. So yeah, so just for you to show this. Okay, so now what? Now we already showed that everything is clear. Up to some detail, right? So there's a detailed exercise for you to show delta is well defined. So it's the same reason, right? That if you want to show it's still well defined, you need to change its difference and the diagram tracing back, and to show that it maps to the same in the co-kernel. Okay. Okay, so yeah, this proof is a little bit long. Okay, so I want to step. So I want to skip. Okay. Okay, so now let's go to the proof. Okay, so now we already have this kernel alpha, kernel beta, kernel gamma, cognitive homomorphism. This is let's call it K alpha, a beta, co-kernel alpha, co-kernel beta, co-kernel gamma, and this is C alpha, C beta. Okay, so the final we already showed that this is well defined. Okay, so we hope to show the exactness. But first step, first step is show K alpha is K alpha, right? So you need to prove that we need to prove the exactness. Okay, so let's see. Okay, so yeah, so you should write down the diagram in the you should write down this diagram in the textbook, in the table. So in some place. Okay, so let's see. Oh, so I know that the top is exact, right? So I know the image FA is a kernel FB, right? So which FB FA is 0, right? It's trivial. Okay, so that means K beta K alpha is 0, right? Because okay, so simple, yeah. K beta K alpha is 0 because K beta K alpha just a restriction of the sub to the kernel. So from here, you know that the image of K alpha, right, is basically sit inside the kernel of K beta. Okay, and so this is just proof this part, right? But you need to show that. So we still need to show that they are actually the same. So conversely, suppose that you get B equals to kernel beta, right? So that means what? That means beta B is 0. You hope to show that there exists something in the K alpha, right? Such that it maps to B. Okay. Let's see. So from here that we know that f of B is 0, right? Because B belongs to sorry, how I'm saying. So if you pick up B to be kernel of K beta, and then you hope to show that there is a something here, right? Can map here. So if B belongs to K beta, that means by definition, right? K beta sub, so beta B still be 0, right? But you also know that so you get K beta B is 0. Right, so K beta is a map, right? K beta is just map of FB, right? So which tell you that FB is 0. So B belongs to kernel FB, right? But exactness, this is image F of A. Okay. So that means that there exists A, right? Such that B equals to FAA. Okay, so you get if you get GA prime alpha AA equals to beta FA. A, right? This is we already use a lot, so this is just commutative, and then which you get beta B, which is 0, right? Since B belongs to kernel, kernel. Okay, so this FA, right, is B, right? But beta B is 0, right? By definition, because B belongs to kernel. Because my definition is that B B is here, right? So B belongs to the kernel of K beta, which is sure that belongs to kernel beta, right? Okay, so also you know that GA prime is injective. The reason is that we already see that I already say that the left exact will implies the injective, right? So GA prime is injective. So if you get GA prime something 0, you get your alpha A 0. Okay. Right. And you know that so A belongs to kernel alpha. So your K alpha A and the F A equals B belongs to image K alpha. And you know that in the kernel, and we get this, right? So this changes sentence to this, right? So we know that the image of K alpha by previous we prove that they must be the same. Whew. Okay, so this is now we prove that this part is exact. Okay, and then next we need to prove the rest is are exact. Yeah, these proof are very lengthy, right? So so I hope to only show. Yeah, maybe I should show. Maybe I should show. Yeah, I mean the proof is very dense. Maybe I should stop here, and let's continue in a future video. Yeah, I mean otherwise the video is so long. Okay, so yeah, this part. So we prove that we only prove one part, and see you guys in the next videos.